The universe is precisely 13.8 billion years old, or so our best scientific methods tell us. But how do you learn the age of the universe when there's no trace left of its beginnings? We see the same constellations on the night sky as did our astronomer ancestors. Familiar star maps are recorded in cave paintings tens of thousands of years old. We could be forgiven for assuming that the universe above is fixed and unchanging. But the Earth was also thought to be timeless until we learned to see billions of years of change in its geological layers. Well, the universe also changes and also had a beginning. In our recent episode, we learned how we calculate the age of the Earth based on radioactive decay in its most ancient rocks. But there are no rocks from the beginning of the universe. There aren't even any photons from the time right after the Big Bang. So today, we go deeper into deep time to understand how we can possibly have learned the birthday of the universe. Actually, you know what? Forget for a moment knowing the age of the universe. Our knowledge that the universe even had a beginning is relatively recent. Let's talk about that first. The discovery of the beginning of the universe corresponds to our discovery that there even is a universe outside the Milky Way Galaxy. Now, this is something we explored in our Stellar series, but it's worth a review. At the beginning of the 20th century, astronomers were arguing about the nature of these faint fuzzy patches of light on the sky, known as spiral nebulae. Were they blobs of gas in the Milky Way, or vast distant groups of stars, other Milky Ways? Or, as Immanuel Kant called them, island universes. We now call them galaxies. It all changed in the 1920s. First, Vesto Slipher found that the spiral nebulae are moving away from us at incredible speeds, based on their Doppler shift, the lengthening of the wavelengths of their light due to their motion. Then, Edwin Hubble figured out the distances to these objects by watching their stars pulse. He located a star type called a Cepheid variable, whose pulsation rate is proportional to its brightness, encapsulated in a simple period luminosity relation. By measuring the pulsation rate, he could calculate its true brightness, undimmed by distance. He figured out that in order for these stars to appear so faint in his telescope, they had to be many millions of light years away. Combining Slipher's velocities, or redshifts, with Hubble's distances, we learned that essentially all galaxies are racing away from us, and the further the galaxy, the faster it seemed to be retreating. This was a shocking discovery. Until then, science had provided no reason to imagine that the universe was anything but static, that it had always been there, and that it had always looked pretty much the same as it looks now. The new picture was far more dynamic. We live in an evolving, expanding universe. The recession of the galaxies makes perfect sense in the context of Einstein's then new general theory of relativity. The Russian cosmologist Alexander Friedmann solved Einstein's equations and found the possibility of a universe that could change in size, a result that Einstein himself dismissed at the time. In fact, even before Hubble's observations, the Belgian physicist and Jesuit priest Georges Lemaitre suggested that Vesto Slipher's observed redshifts could be a sign of the universe's expansion. Lemaitre put forward the idea that the world began in a state that he referred to as a primeval atom. Think of it this way: if the universe is expanding now, then in the past it was smaller. Rewind the clock according to the raw Friedmann equations, and there's no alternative. The universe must have once been in an extremely hot, dense state and expanded from there. Astronomers call this the Big Bang model of the universe. Now, the name Big Bang was coined by the astronomer Fred Hoyle during a 1950 BBC radio broadcast, but not to popularise the idea, rather to mock it. Hoyle was the last great holdout against the idea of a dynamical universe with a finite age, for a long time sticking with his own steady-state model. This idea that the universe has a beginning brings to mind the creation stories of various mythic or religious traditions. Some have even tried to claim that the Big Bang is a validation of their tradition. Pope Pius XII certainly thought so. But priest or no, Georges Lemaitre himself disagreed. He stated, "As far as I can tell, such a theory remains entirely outside any metaphysical or religious question." So, if we can predict that the Big Bang happened by rewinding the Friedmann equations, surely we can also predict how long ago it happened. Think of it this way. If a particular galaxy is racing away from us, and we know how fast it's moving and how far away it is now, we can figure out how long ago it must have taken to cover that distance. In other words, how long ago was it right on top of us? Even doing that for a single galaxy gets us a rough estimate of when the Big Bang happened. However, to accurately calculate the age of the universe this way, you need to account for a few more things. First up, there's the fact that galaxies aren't only moving away from us due to the expansion of the universe, they also have random motion as they're tugged by the gravitational fields of nearby galaxies and clusters. We can deal with these peculiar velocities just by averaging over many galaxies. Then there's the fact that the expansion rate has changed over time. You can't just assume that the galaxies were always moving at their current speeds. Now, we'll come back to that later. For now, we'll see that we can do a lot just by having a good idea of the current expansion rate. That rate is encapsulated in something called the Hubble Constant, which just tells us how fast a galaxy is moving away from us given its distance from us. The more distant, the faster it's moving. In the near century since Edwin Hubble's great discovery, thousands of astronomers have devoted their lives to measuring the Hubble Constant. And a big part of the motivation is that it tells us the age of the universe. In fact, if you take the fraction of 1 over the Hubble constant in the right units, you have the age of the universe, at least assuming no gravity. And if your Hubble constant was determined by looking at lots of galaxies, then it gives you an age averaged over lots of galaxies, and that averages out those pesky peculiar velocities. And when astronomers did this calculation in the early 1930s, they figured out the universe is a bit less than 2 billion years old. Even then, that figure didn't sound right, because by then, geologists had already found rocks here on Earth that were at least 3 billion years old. So there was a problem. But it wasn't a problem with the theory, it was a problem with the observations. Edwin Hubble had got the distances to the galaxies wrong. It turns out that Cepheid variable stars come in two types, with two different period luminosity relations. Hubble had observed a brighter variety of Cepheids in distant galaxies, but then used a period luminosity relation measured from a different fainter class of Cepheids that were measured in the Milky Way. So he measured the periods of his Cepheids and then calculated what he thought was their true luminosities, but the numbers he got were too low. He thought they were intrinsically fainter than they really were, and so concluded that they had to be closer to us than they really were. In fact, he got distances wrong by about a factor of 2, too small. Overnight, the universe doubled in size. This whole two different types of Cepheid issue was figured out by Walter Bahaar. In 1943, beneath the dark skies of wartime blackouts, he used the 200-inch telescope at Mount Palomar to peer deeper than anyone had before into the Andromeda Galaxy. With a newly calibrated Cepheid period luminosity relation, and also incorporating other distance measures, which I'll come back to, Bahaar calculated a new age for the universe. At a conference in 1952, he announced that it must be 3.6 billion years old. At last, the universe was older than the Earth, although still a way off our modern value. To understand the next step in improving this number, I need to explain another method astronomers had been using to get distances to galaxies, and so to calculate the Hubble constant and the age of the universe. It's similar to the Cepheid method because it's based on comparing the expected true brightnesses of stars with the apparent distance-dimmed brightness. It seems fair to assume that the brightest stars in any galaxy have pretty much the same average brightness from one galaxy to another. So, if the bright stars in a given galaxy appear faint on average in our telescopes, it means the galaxy is further away. If they appear brighter, then it's closer. But astronomers had originally made an awkward mistake. They'd been counting bright clouds of hydrogen gas, so-called H2 regions, as stars, which threw their numbers off. It was a young astronomer named Alan Sandage who figured this out. Sandage was a student of Walter Baade and also worked closely with Edwin Hubble. By eliminating the problem with H2 regions, he came up with a new age estimate for the universe, 5.5 billion years. That was in the 1950s. As the decade went on, Sandage continued to revise those estimates. He eventually concluded that the expansion rate of the universe, the Hubble constant, was about 75 kilometers per second per megaparsec. Now, don't worry about those units too much, but it gives us an age of the universe of around 13 billion years, assuming no gravity and no dark energy. But that's remarkably close to the currently accepted value. Sandage figured out that with gravity playing its part to slow down the expansion, the universe must have been expanding faster in the past, and so it should have taken less than 13 billion years to reach its current size. He estimated its age as between 7 and 13 billion years old. Now, there were some moments of confusion. For a while we thought that we'd found globular clusters, ancient dense groups of stars, that were 15 billion years old, as bad as finding rocks older than the universe. But as our understanding of stellar evolution improved, those ages came down to under 13 billion years. Now, to arrive at our current very precise value of 13.8 billion years, you need to take into account the effect of matter slowing down expansion through its gravity, and also the effect of dark energy speeding it up. Those can be put into the Friedmann equations, and a bit of calculus later gets you an age. The real hard part is figuring out how much of all that stuff there actually is. The mass of the universe, which is mostly in dark matter, can be found by adding up its gravitational effect in galaxies and in galaxy clusters, and also by tracking the past expansion history of the universe to observe the slowing effect of all of those galaxies on the whole universe. It was in an attempt to do the latter that astronomers discovered the anti-gravitational effect of dark energy and had to start adding that into their equations also. But that's a story for another playlist. Long story short, the accelerating effect of dark energy counters the slowing effect of gravity to ultimately give us an age of the universe very close to the roughly 13 billion years that we get from assuming the expansion rate hasn't changed at all. These days, the gold standard for measuring the age of the universe is to get the matter content and the dark energy content and the expansion rate and more from one source, the cosmic microwave background radiation, the oldest light that we can see, released when the universe was a mere 400,000 years old and much, much smaller and hotter than it is today. And for the details of the cosmic microwave background and how we use it to calculate the contents of the universe, well, guess what? Here are some episodes that we prepared earlier. Based on analysis of the cosmic microwave background map produced by the Planck satellite, we get the relative amounts of matter and dark energy and a number of other quantities important for plugging into the Friedmann equations, which define the way the universe would expand in the many billions of years following the release of that radiation, and also how it had expanded before that time. There are other approaches to getting the necessary numbers to fuel the Friedmann equations, and despite some intriguing conflicts, different methods are mostly in agreement. They converge on a single number. It's been 13.8 billion years since the fiery beginning of time as we know it, the birthday of space-time. In the current difficult circumstances, every little bit of help is huge. There's no way we could be so consistent in our releases if it weren't for your support, and that's especially true of our Patreon supporters. Your contributions, large and small, are a big part of what makes this show possible. Today, I'd like to give an extra huge thank you to Radu Negulescu, who's supporting us at the Big Bang level. Radu, as an official representative of both space and time, I want to thank you on behalf of the universe for ensuring that we keep paying attention to it, despite everything. So, last time we talked about wormholes, one of the most awesome entities in general relativity that probably don't exist. Devansh Rana asks, can wormholes exist without black holes, i.e. without an event horizon? Well, the Schwarzschild wormhole definitely has an event horizon, although at its most open, entering that event horizon ejects you into the parallel universe. You can construct a wormhole in general relativity that does not have an event horizon, but you need negative energy to do so and to keep it open long enough to traverse. The reality is that in general, traversable wormholes probably can't exist, and having an event horizon is one way for the universe to enforce that. Magnum Polmatier summarized that better simply with, sort of, not really. Lucid Moses asks a good one. Is the tube connecting the ends of the wormhole meant to be in 4D spacetime or somewhere else? Well, the answer is sort of somewhere else. The tube Lucid refers to is in the so-called embedding diagram of the wormhole. It's really a 2D slice out of 4D space-time, with time and one dimension of space discarded. But the diagram has 3 dimensions, so what is that third dimension? It represents the amount of stretching of the fabric of space-time, the strength of the gravitational field, if you will. Same as the rubber sheet analogy in which a massive body depresses that sheet. What dimension is the sheet depressing into? Well, none. It's a representation of the curvature of space-time. Lala Fafa asks why the wormhole tunnel is thought to be shorter than the normal space path between wormhole ends. Well, the simple answer is because it can be. You can write down a solution to the Einstein equations in which the wormhole throat is short, and it has no relationship to the actual distance between wormhole ends. So you build a wormhole with a short throat and then move its ends far apart. That doesn't change the length of the throat. So there's your shortcut. In the case of the Schwarzschild wormhole, the distance has to be short. When the wormhole is fully open, the event horizons of the wormholes intersect, they coincide, pass through one event horizon, and at that instant in time, you exit the other. New Message actually puts all of this into perspective. Fast interstellar travel? I'd settle for a leisurely stroll down to the grocery store at this point in the lockdown. Despite the absolutely fascinating topic of wormholes, most questions were about the cat that walked through the background during the last comment responses. Now, many of you were properly introduced to Simone during last week's live stream. If not, you can go and meet her there. It's still available to watch. But anyway, yeah, that's Simone. She loves crawling into boxes whenever possible, I assume to test quantum theory, miraculously emerging definitely alive every time. She's become a pretty hardcore Everettian, always trying to convince me of the reality of the quantum multiverse and how there are way more treats in other branches of the wave function. There are plenty of treats in this one, Simone.